Hey everyone, and welcome. Have you ever been staring at a network trace and just scratched your head? Like, why is this server getting hammered with multicast traffic it never even asked for? Well, today we're going to crack that case. It's a really cool little mystery hidden deep inside how our networks actually work.
Yeah, that's the big question, right? You've done everything by the book, your multicast groups are set up perfectly, the subscriptions are all in order, and yet, here comes this flood of data you don't want. It feels like something's broken, like it has to be a bug. But, and this is the wild part, it's not. It's actually an intentional quirk, a feature, of how networks translate information.
So where does this all start? Well, it boils down to a simple problem. Different parts of your network are speaking totally different languages. They've got different jobs to do, and to do them, they care about completely different kinds of addresses. And this is where you can really see that communication gap. Think about it. Up at layer 3, you've got your routers and your servers. They're thinking in IP addresses. They're asking the big picture question, what group is this traffic for? But then you go down a layer, to layer 2, where the switches live. Switches, they only speak MAC addresses. Their world is much simpler. All they care about is, where does this specific frame go right now? They have no clue what an IP multicast group even is. So you've got this problem. To make it all work, you need some kind of translator, a rule that can take that high-level layer 3 IP address and turn it into a layer 2 MAC address that a switch can actually understand and use. I mean, without that, your only other option is to just blast the multicast traffic everywhere, like a broadcast. And that would be a disaster for performance, totally defeating the whole point of using multicast in the first place. Okay, so how does this magic translation, this IP to MAC code, actually happen? Let's get into the nitty-gritty. The formula itself is surprisingly simple, but it comes with a massive side effect. It all kicks off with a special prefix, 010050E. As soon as a switch sees a MAC address that starts with this, it's like a big flashing sign that says, hey, pay attention, this is a multicast frame. It's a reserved address range set aside just for this job. Okay, so if the first part of the MAC is always fixed, that means all the important, unique information from the IP address has to get crammed into what's left. And here's the kicker. There are only 23 bits of space left to work with. Just 23. And this is exactly how they do it. The system literally just takes the last 23 bits of the multicast IP address and, bam, pastes them right into those last 23 bits of the MAC address. It's a simple copy-paste. But that should make you wonder, what about the rest of the bits from the IP address? Where do they go? And that is the heart of our mystery. That simple, straightforward copy-paste job is what creates the entire problem, the overlap problem. See, when you look at an IPv4 multicast address, there are 28 bits available to define a unique group. 28 bits of crucial, identifying information. But like we just said, the MAC address only has room for 23 of those bits. You don't have to be a math genius to see that something doesn't add up here. Here's the absolute key. Every single time this IP to MAC translation happens, 5 bits of information from the original IP address are just gone, thrown away, poof. Think about it like this. It's like trying to save a full phone number, area code and all, but you only have enough space for the last 7 digits. Of course you're going to have overlaps. And this slide shows you the result perfectly. Just look at this. We have 2 totally different multicast IP groups, but because the part that made them different was in those first 5 bits, the bits that get dropped, they both end up with the exact same MAC address. As far as the switch is concerned, these 2 completely separate traffic streams are identical. Okay, so we've cracked the how this happens, but now for the big question. So what? Why does this geeky little detail actually matter on a live breathing network? This whole situation has a name. It's called MAC aliasing. And remember, this isn't a bug. It's not something you configured wrong. It's a built-in, unavoidable side effect of how this was designed. A single MAC address can end up being an alias for as many as 32 different IP multicast groups. 32! And this brings us full circle, right back to the mystery we started with. Your server asks for traffic for Group A. Then, somewhere else, a stream for Group B starts up, and it just happens to have the same alias MAC address. The switch, which only sees the MAC, says, oh, you want this, and forwards both streams to your server. Now your server is getting flooded with traffic it doesn't want, which chews up bandwidth and forces the CPU to work overtime just to inspect and throw away all those useless packets. It's a nightmare to troubleshoot. So here's the deal. You can't fix MAC aliasing. It's baked into the standard. It's not going anywhere. But what you can do, and what you absolutely must do, is manage it.
And your number one tool in the toolbox for this is something called IGMP snooping. IGMP stands for Internet Group Management Protocol. When you turn this feature on, your switch suddenly gets a lot smarter. It starts snooping on the subscription messages between your devices and routers. It builds a little map so it knows exactly which ports need which multicast streams, instead of just blasting them out everywhere. It is a huge, huge improvement.
But, and this is super important to understand, IGMP snooping is a filter. It's not a fix for the underlying problem. If one of your servers subscribes to an IP group and some other traffic starts up with an aliased MAC, the switch is still going to send both streams to that port. Snooping helps contain the chaos, but it can't solve the fundamental MAC address overlap.
So, what's the game plan? How do you actually deal with this in the real world? It really comes down to smart network design. First off, you've got to plan your multicast IP address ranges carefully to avoid these overlaps in the first place. Sticking to the administratively scoped 239 range is a great start. Then, like we said, turn on IGMP snooping on all your switches. All of them. And keep an eye on your traffic flows. If you see weird spikes, it could be aliasing. Finally, use things like VLANs to break your network up into smaller multicast domains. You really need to do all of these things together.
And that brings us to the big takeaway here. What we've been calling a problem or a flaw isn't really a flaw at all. It's a design compromise. Back in the day, the engineers who created this made a choice. They went with a super simple, fast formula that would be easy to build into network hardware. And they decided that the side effect of MAC aliasing was an acceptable trade-off. It was a conscious decision to choose simplicity over perfection. And that's a really interesting thing to think about, isn't it? This whole system is a perfect example of an engineering compromise that was good enough to become a worldwide standard that we all depend on. It makes you wonder, what other clever but maybe not so perfect designs are out there, quietly powering the technology we use every single day? Something to think about. Thanks so much for joining me.